Hello, everyone, and welcome to the Mindscape podcast. I'm your host, Sean Carroll. We had a AMA question a couple of weeks ago, earlier this month, that I'm not sure I did a great job of answering. I tried to give an impression of what was in my mind. The question was about the difference between complexity in the sense of complex systems research versus simply being complicated. I've actually invoked this distinction before. They're not the same thing, but neither word really has an agreed upon single definition. So I kind of said that, and I said, well, it's up to whoever is speaking. You can mean different things. But it occurred to me later, when thinking about today's podcast that you're about to hear, that there is sort of a single thing you can put your finger on that really distinguishes simply being complicated from being complex in the sense that we use it, which is complicated means there's a lot of stuff going on. Complexity happens when there's a lot of stuff going on and those things interact with each other, so that in some sense, the whole system of interacting complicated things going on forms a whole. There is some notion of the system arising out of the smaller pieces in a way that still makes the pieces be important. So it's different than the very, very simple-minded notions of emergence that we have sometimes in physics, where you have, atoms coming together to make a fluid. That's absolutely true. You have many, many, many atoms, and they come together and they interact to make a fluid. But then once you have that fluid description as a gas or a liquid or whatever, you can forget about the atoms, right? You can sort of average over what all the atoms are doing and get a pretty good higher level description of what's happening. In a complex system, the little pieces that come together to give you the whole continue to matter. In a country, a nation state, the individual people continue to matter. In an economy, the consumers and producers matter, as well as the rules and regulations that guide their actions. And today's system, today's complex system that we're going to be talking about, is the Earth's oceans. And they are themselves complex, but of course they also play an enormous role in the complex system, which is the Earth itself and the Earth's biosphere in particular. You've all heard the numbers. Most of the Earth's surface is covered with water, a little bit over 70% of it. The oceans are where most of our water is on Earth. Some of it is on rivers and lakes or in the atmosphere, but the oceans is most of it. And you may also have heard that our climate is changing. It is completely unsurprising that the oceans have a huge effect on our climate. And it is also completely unsurprising that we humans are having a huge effect on our oceans. So today's guest, Helen Czerski, is going to tell us about that. She is a physicist turned oceanographer, perfect kind of Mindscape guest. And she has a book called The Blue Machine: How the Ocean Works. And the blueness, of course, is something you've probably already heard about the ocean. The machine aspect is because the oceans are not just sitting there. They are moving. There are many moving parts, as complex systems are wont to do. And also, there is input and output, right? The oceans are interacting with the atmosphere, with the radiation from the sun, with the tectonic motions of the Earth's plates, and, of course, then the oceans act back on the Earth itself, the life in the oceans, and then the life here on land. So it's a wonderful example of a good science problem, a good example of a complex system, and of course, a system that means a lot to us human beings in our lives now and in the immediate future. So understanding it a little bit better, understanding the challenges that we human beings have put on our oceans is an important task. So let's go. Helen Czerski, welcome to the Mindscape podcast.
Thank you for having me on.
So I thought I would begin, inspired by a little mention in your book. There's this saying that goes around that we know more about the moon than we know about the deep sea ocean or the bottom of the ocean. So how do you feel about that saying?
Oh, now that is brave of you. Let's get the rant out of the way right at the beginning. Well, it's a shame I haven't got, this is a podcast, so we don't have slides. But when I make this point on a PowerPoint slide, there are a lot of flames burning that statement up, because I basically think no one should be allowed to say that ever again. And I will give you the short version of the rant, which is basically that the massive problem with that statement is that every time anyone repeats it, they are reinforcing this idea that the deep ocean is just equivalent to a piece of dead rock that's not changed for 2 billion years. And it's so much richer and more interesting. And there's so many more things going on. And there's complete ridiculousness going on down there. And it's interesting and rich. And so basically, there's so much more to know about the deep sea than there is about the surface of the moon. And so to complain that, well, we haven't mapped every square centimetre of it to the accuracy that we have on the moon, which of course is relatively straightforward because light, is a very useful tool, and you can't use light in the ocean in the same way. Certainly not over any distance. So to reduce it to only being a map, where the only thing that matters about it is the shape, the topography of the bottom, and to ignore everything else is just rubbish. And it annoys me because it's you got to have your little rant about something, but actually it's a really serious point, I think, because we continually underestimate the ocean. And the reason we underestimate it is because we dismiss it in this amazing variety of ways. And this is just one of the ways. So yes, I'm glad you got that in at the beginning, because if people listening to this podcast take away one thing, please never compare, never say we know more about the moon than we know about the deep sea ever again, please, because it's not true.
Well, it's also a good reminder in astronomy terms, what we would say is the time domain is very important here. There is no snapshot you could possibly get of the deep sea that you would say, okay, that's it, we're doing pretty well.
Yeah, that's right. And the ocean is an incredibly dynamic place. And of course, it's dynamic on lots of different timescales and this is a point that certainly cosmologists will be very familiar with, that we privilege our own timescales and size scales, and we're very arrogant as humans that we think they're the only ones that matter, when actually if you slow things down or speed things up, there's lots of things happening. It's just not apparent to us. And of course, life itself is doing all sorts of interesting things on lots of different scales. And so actually one of the things I didn't mention about, just an example of a thing that happens on the deep sea, in the deep sea, that is quite memorable, but the deep sea is full of stuff like this. There is a type of worm that lives with its head down in a sponge. So a sponge is an animal. It's just about got enough life in it to count as an animal, full of holes. And so this worm comes along. When it's a juvenile, it sticks its head right down the bottom of the sponge and it embeds itself. And then as it grows, the tail grows upwards through all the holes in the sponge. But it doesn't just grow, it branches. And so as it grows, it keeps branching until eventually it's got thousands of little tails that are all poking outside of the sponge. It reaches the edge. But they're not stationary. They move around. There's videos of this, and they're all kind of poking, they're sort of moving around the surface. So you've got, this worm has 1,000 little anuses, basically. And there's only 3 worms that do this branching thing. It is very weird, even in nature. But then the thing is, so how does a thing like that come to mate? So, because obviously it's not going dating. It's very embedded in its sponge. It's not getting out of that. So what it does is that all the little anuses at a predetermined time grow eyes, and they get rid of the digestive apparatus and they grow gonads, and then they break away and they swim off to the surface and carry the eggs and sperm with them. And this is coordinated, and so they all get on with the mating at the surface, and then the juveniles float back down and find another sponge. And you do not get that on the moon. There is more science in that one worm than there is in the whole of the moon. And the moon's very nice.
Yeah,
it's a very nice place. I have no objection to the moon. It's just not as interesting as the ocean.
And the one technical question I have to ask here, does the worm ever become topologically non-trivial? Like, do 2 little parts of the worm ever rejoin, or is it always just going to be a tree?
I think it's always going to be a tree.
Okay.
I haven't examined every worm, so obviously I cannot tell you that it's definitely not ever happened, but I think it's unlikely. So I think these worms, there's no joining up again. The topology doesn't change once it gets started.
It does make you think that the people who make science fiction TV shows and movies lack imagination a little bit. Like, they should go down into the ocean and get inspired for some real fun alien biology.
Well, there is a thing. I've never quite managed to back this up, but there is a rumor that the alien in the Alien movies was inspired by some kind of deep sea zooplankton, sorry, nearer the surface, so not in the deep sea, but the near surface ocean. But I've never really managed to back that up. Although I can imagine that if you want to design any kind of monster, I mean, it's a very sensible thing to go to the local library and look up what nature's already done, right? It might give you some ideas. So, yeah, I mean, it is, I think in at least some cases, it is the case that our idea of science fiction is inspired by ocean fact.
So let's back up a little bit. You've been described as an accidental oceanographer. You started in physics and then somehow went through bubbles before ending up in the ocean. How did that journey happen?
Yeah, I did all my physics degrees at Cambridge and got a PhD in experimental physics, in experimental solid state physics, really studying explosives. And so it's a very, classical physics education. But the thing that always interested me was the things that I can see. I wanted to be able to relate the physics I was studying to the things that I can see. And so the theoretical physics I found a bit frustrating because I could never find out, right? I understand that the mathematics is very beautiful and that there's a satisfaction in that, but I wanted to kind of see and play with the things that I was studying. And that, so it's almost all classical physics, but it's complicated because all the forces have a similar level of influence. So instead of it being just a trade-off between two forces or maybe three on a good day, you've got everything in there that is, kind of all trading off against each other. And so you get these really complex and rich situations. And so I wanted to do that kind of physics. And even back then at the Cavendish, it's the Cavendish Laboratory in Cambridge. It's got a big bit of sort of quantum mechanics and a big bit of astronomy and cosmology. And then there's this messy stuff in the middle, which was sort of across the other side of the building in solid state physics. And so that's what drew me in, and that's what that kind of physics is what sent me out into the world, really. So I used a lot of high speed photography to study explosions and solid state physics and solid state phase changes. And the high speed photography took me. I didn't want to blow things up for the rest of my life. Very boring. Don't let anyone tell you it isn't. Especially the clearing up. No one ever mentions that bit. So I went looking for something I could do with that, and bubbles came along. I did spend, when I finished my PhD, 6 months just reading every copy of Scientific American and Nature and New Scientist that I could, looking for a topic. There must be somebody who's studying this messy physics in the middle. And so I found it in the world of bubbles, and high-speed photography took me there, and then I learned acoustics, and then that took me into the ocean, basically entirely by accident. And the thing about it is that I was that kid that read, I'd read all the science books, I'd read the books that were out there. I thought I had an approximate idea of all the topics that there were in science. And then at the age of 26, I rock up at the Scripps Institution of Oceanography with a PhD in physics. And I suddenly discover no one has talked to me about the ocean. It's ridiculous. And as soon as I saw it, there was this moment where I watched my colleagues push an experiment out into the ocean, and I suddenly understood that the water was doing things in a way that I hadn't before. And as soon as I thought about that, obviously, we are looking at a liquid engine. Why is no one talking about this? It's clearly the biggest story on Earth. And then I went round, then I had to teach myself effectively. And I went round Scripps, which is this big oceanography institution. And there was, towards the end of my time there, I did go around knocking on doors saying, so there's this ocean thing that I haven't got any degrees in that you all study. Please, can you recommend me a book? And I got so many interesting books. Not a single one of them was about the physics of the ocean, not one. And I must have got about 10 or 12 book recommendations. And so it kind of stayed with me, this bug, that there's this massive story. It's staring right at us every time we look at the blue planet and call ourselves a blue planet, and we never actually look at it. And it's astonishing. Our ocean blindness is astonishing. So yeah, I became an oceanographer by the back door. And there's a lot of physics in the ocean. It's really complicated. It's full of turbulence, quite apart from anything else. And so it's not the case that you can start from first principles and deduce what the ocean is going to do. It's doing far more interesting and intricate things than we would generally suspect. So yeah, it's growing. People are getting more interested in it now. Good. But it did feel very neglected.
I do think that this is a big conceptual point about how science is done that maybe is not as appreciated as it could be. You know, the physics paradigm is to simplify everything as much as possible until we can get down to some solvable model and then hopefully put the complications back in later. But there are whole sets of systems, certainly in the biological world, but as you're pointing out, even in the sort of it's a very physical world there in the ocean, and it's nevertheless super duper complicated and nonlinear and interconnected in a way that a ball rolling down a plane or two electrons smashing together at a particle accelerator really are not.
It drives me nuts, actually, and I find it very hard. I find it very difficult to understand why the physicists I was working with were so resistant in a lot of cases to this complexity. And the early examples were in acoustics because that's what I came to first. But actually, the more serious example, I think, so the application for what I do now, so I study breaking waves and bubbles, and because they're at the ocean interface, and anything that crosses the interface has to sort of go through all this complexity, right? So if you want to understand how much gas is going up and down, you need a concentration gradient, and then you need some term to do with the processes, which tells you how fast it's going to go, how fast the transfer is going to go, and that's the bit we're not very good at. And so I remember that one of the first ocean conferences I went to, going to one of the talks, and there was this enormous debate. So basically the way this works in the ocean is that we have traditionally tended to characterize it by wind speed. So when the wind is higher, there are more breaking waves, there's more turbulence, and so the speed of that transfer goes up. So you tend to compare it with wind speed. And then you have this transfer coefficient, doesn't really matter what that is on the y-axis. And people were drawing these lines through all these dots and trying to make it, they were arguing, is it wind speed squared or is it wind speed cubed? And they were having these arguments. And I was like, it's obviously neither one. Why is everyone wasting all this time in this conference debating whether this thing is one of these very fixed things or the other one? Because it's clearly nothing to do with either. And the resistance to suggesting that there's something more going on was really interesting. And there are practical reasons for that. We're good at measuring wind speed. It's nice if we can parameterize everything in terms of wind speed. But I think it's becoming less now, like systems thinking is becoming a bit more appreciated. But I'm a mechanisms person, right? I'm not interested in the fact that it's squared or cubed. I'm interested in the mechanisms that are driving it. And then you have to deal with messiness. And you're right that I think there is this thing in physics of beauty. We know it's right because it's beautiful and it's elegant. And that's how you know, especially as an undergraduate, like solving sort of those very satisfying problems where you can come up with an equation that predicts something. And the world's not like that. Sorry,
but
it's much more interesting. Isn't that great? And so the ocean is full. The ocean is a great example of one of these systems where you can't deduce. The reductionist approach will only take you so far. And then you might have to get a biologist in and they'll make it really messy.
We will get there, but let's get into this physical complexity of the ocean. Let's get into some of the details here. I mean, I guess the first thing to confront is the fact that it's three-dimensional, right? It's not just the surface, and there are layers in the ocean. How well this sounds like me being a physicist trying to oversimplify things, but how far can we go talking about the ocean being divided into different layers?
Well, actually, I'll give the physicist that one because that one mostly does make sense. Like the ocean is basically driven by density. The ocean engine, like the parameter that is driving the movement, any vertical movement in the ocean, is density, and so it's the interesting thing about it is that the differences in density are actually relatively small. If you take fresh water that's quite warm, you've got a density of around 1,000, depending on the exact temperature, 1,000 kilograms per meter squared. And then if you make it saltier and you make it colder, you make it denser, but not much denser, like a few percent at most. And yet, for these enormous bodies of water, tiny fractions of a percent of difference in density are enough to make them layer up. And so the surface of the ocean has this thing that we call the mixed layer, because, oceanographers are literal as well, which basically is the surface. It's the kind of boundary layer which is well mixed. And so it's close to the surface, it gets sunlight, it's warm because it gets sunlight. It's got things living in it, lots of them, because it's got sunlight, and it's kind of separated from everything below because it's warm. And so it doesn't mix. The timescales are not long enough. Energy is being put in faster than it's kind of diffusing through. So you've got this very clear layer at the top, which ranges depending on where you are around the world and what the weather's doing, from sort of 50 to 100 meters ish. And then down below, you've got these other much thicker layers that might be a kilometer or two, and they are much smaller density differences, but they're very clear. You know, you can. One of the things that an oceanographer does, it's the first time. It's almost the first thing we do whenever we arrive anywhere. It's kind of old fashioned in a way, but it works. Is you lower this thing down over the side of a ship called a CTD, which measures salinity, temperature, and depth, except for completely unimaginable reasons they decided not to call it an STD. So it's a CTD for conductivity. And it is quite astonishing. You lower this thing down through the water and you get real-time readings back on the ship. So you can see temperature and salinity. And there are really clear layers almost everywhere in the ocean. As it goes down, it'll be almost the same, and then it'll switch. And over the course of maybe 10 meters, it suddenly becomes a different temperature and salinity. And then maybe it'll change gradually for a bit. And you really clearly can see these layers. And then you go to places like the Baltic Sea and it's completely bonkers and there's loads of layers and it's all very weird. But it definitely is stratified. That's the word we would use. It's got these quite strong layers. And the thing about that is it means that most water moves horizontally. It moves sideways because there isn't enough energy to mix it up and down. And so there are only a relatively small number of places where water from the surface will become dense enough to sink, or water from below will sort of mix its way up. And so you've got this... there's a lot of very fast horizontal movement near the surface where the winds are pushing things. And then underneath, you've got this much slower density driven thing, which interacts with deep sea mountain ranges, underwater mountain ranges, and goes across Great Plains and sort of interacts with sea mounts. That generates turbulence. It mixes everything up. And so water has character. And then it's not just the temperature. So the temperature and salinity set where the water is, but then within that water, it has a chemical signature of nutrients like phosphorus and nitrogen, and also trace elements like gold, for example. You can draw these amazing maps of things that are in parts per trillion sometimes distributed around the world, and there are patterns. So every water packet has a character, and it carries it with it as it moves along. It kind of carries that character with it. And so there is this physical structure that is all moving at different speeds. And that sets the scene for everything in the ocean. It makes the ocean a three-dimensional place, not just a sort of void with a coordinate. And you go here and the coordinates, the same as a couple of coordinates further along.
The point about density is interesting because I absolutely would not have guessed that. I maybe, again, my naive physicist thinking is water is more or less constant density, but the pressure can change a lot. But of course, you're pointing out that the temperature and the salinity change considerably, and that or change a little bit, but have considerable implications, I guess I should say. Is it at least uniform? Is it monotonic? Does it just get colder and more saline as we get deeper and deeper?
No, it gets denser, but not always the same for the same reason. So for most of the ocean, if the big ocean basins, it is generally driven by temperature. So you get varying salinities perhaps, but generally temperature is the big beast in the room, and it gets colder as it goes down. And so the deep ocean, probably around 4 degrees C generally. And the surface depends on where you are around the planet. But the Arctic is different. So the Arctic, so there's two classes. You can class these ocean layers as driven by temperature or driven primarily by salinity. And in the Arctic, it's driven by salinity, because at the surface you have fresh water, because you've got ice melting and thawing, and that gives you a source of fresh water. Underneath it, there is a salty layer that is warmer. But because it's so salty, it's dense. And so it sits in the middle under the ocean. And there's actually enough energy in that layer to melt all of the sea ice, like not just now, but 100 years ago. But that warmth, that heat doesn't reach the surface because it's kept it's in this salty layer, right? The density keeps it down. So it's always a combination of temperature and salinity, but it can be driven by either one. And actually, this is one of the questions when people are looking at oceans on other planets, because of course if they're big enough, will also have some kind of dynamics. And the question that drives that is do you drive that ocean do you drive your layers, predominantly by temperature or predominantly by salinity? Because you get quite different kinds of ocean dynamics in both those cases. So we have mostly one half of that on Earth, but on other planets or moons, you could well have a mixture.
I had not thought of that. I mean, I know that Europa, for example, the moon of Jupiter, has an enormous amount of water hidden underneath ice, but we don't know much about its structure. So you oceanographers are going to have to figure out the theory of it so that we can predict it before we go there.
Well, people do work on that, but of course we have a data point of one effectively. I mean, our ocean is quite complicated, but we've got a narrow set of a small area of the parameter space to actually test. Yeah. So I'm sure we would learn stuff from other planets as well. And of course, one of the reasons it matters on Earth is that when we're looking at how the ocean changed in the past, because of course the way this engine turns now is not necessarily the way it turned in the past. The rules are the same, but because the continents have moved, for example, and the amount of sort of energy arriving at Earth, the balance of the energy and things like that have changed. Earth's ocean could have functioned differently in the past, and these layers would have been different in the past. And so there is a period in Earth's history, and I can't remember how long ago it was, when the deep ocean was actually quite warm because it didn't have this overturning circulation that pushed cold water down into the depths. So it's also a question of time on Earth. You go back to that, things change in time, not just in space. And so even on Earth, the ocean can function in different ways. It's just we've got one version right now.
And okay, so we have these layers, we have stratification based on density, but then, as you say, there are movements, mostly horizontal. In fact, you have a map right at the beginning of the book of what the currents are. It always struck me a little bit that the currents are that well defined that you can make a map of them. They don't. Do they not change that much from day to day? Is it so predictable?
Well, yeah, well, there's some averaging involved here. So it depends on the time scale and size scale at which you look. So when you look at those maps, so the cover of the book, the hardback in the UK, which was my favorite cover, don't tell my American publisher, has the Spillhouse projection on it, which is the way of unwrapping the globe so that the ocean all stays connected. And Spillhouse, who was quite an interesting so-and-so, designed this map in 1942. And he said that in order to see the land, we always cut the ocean. So in order to see the ocean, we must cut the land. So he cut the land in order to unwrap the global map so you could see the ocean. And so there you can see these big circulating currents that are all connected, that go sort of around and around the ocean basins. And they're averages. So that's a time average. You've taken out basically all the small scale fluctuations, and then you can see these big currents. But if you take out if you sort of do your frequency, I don't know how physically, how comfortable your audience are with the physics of this, but I suspect they're a pretty clever bunch. So if you filter instead to the sort of higher frequency alteration, so you look at the smaller scale, the smaller spatial scales and the faster time scales, then you see a lot of eddies. So if you look at the surface ocean on time scales of days, for example, you see there's these little swirly things everywhere of lots of different scales. And so you can't, on those spatial scales, you can't really see the big ocean gyres because it's all overwhelmed by these little, much smaller swirly things. And of course, then when you go down even further, then the motion at the surface is driven partly by the wind pushing on the surface and generating shear, partly by wave action generating Stokes drift, and then turbulence at the surface from storms and stuff like that. So everything depends on the scale at which you look. It's all about, as you zoom out, you see different patterns as you go out. But the big patterns are important because they are shifting heat, especially heat and nutrients around globally. So that's the big beast behind everything, and everything else kind of sits on top. So yeah, I mean, but ocean creatures there are plenty of turtles and the European eel, for example, that will hitch a ride on those big gyres, on those systems that are too slow to see at any one moment in time, but they definitely do it and they definitely arrive. So, even a turtle can do that averaging basically well enough to see an ocean gyre.
But this sounds very complicated and should make you want to switch to particle physics.
No, I like the mess. You can keep the particle physics. Thank you very much.
There is a lot of the mess.
I get to play with turtles.
That's true. No, yeah. I mean, Caltech, there were turtles in a little koi pond, but it's not really part of the day-to-day work of the institution. You mentioned this. I'm biting my tongue because I want to get into, the various ways which this dynamism happens and we understand it. But you alluded to a little bit how we learn about it. And I do want to, give some airtime to the experimental side of things. How do we know all these wonderful things you're telling us? Is it mostly because we human beings go down there and visit, or do we send robots, or do we just use remote sensing?
It's varied over time. And of course, in the centuries before people made the sorts of standardized measurements we would make today, mariners of many civilizations found this out by experience. And so humans are voyagers on the ocean as well. So the second half of the book is split into messengers, passengers, and voyagers, the things that kind of travel through the ocean in various ways. And humans are also voyagers. So I think human observation, you can see a lot if you know how to observe, but we've almost completely lost those skills because now everyone's got GPS and, compasses and things. But in terms of how we have found out about the ocean, for a long time, the way oceanography worked was basically that you went out in a boat and then you dangled something over the side on a piece of string, because that was the only way you could access the ocean. And actually, one of the big breakthroughs came with the invention of something that is a sort of bottle that was now there's a version called a Nansen bottle, but it's a very clever. There were earlier versions, none of them really worked very well, but this thing is it's kind of like a tube, like a bit of drain pipe, and the top and the bottom are open, and it goes into the water vertically. So as it goes down, the water just kind of flows through the tube, and then the mechanism that was invented that made this thing work is that what you want to kind of snap lids on the top and the bottom at the same time, right? So you send it down, you trap some water at that depth, you bring it all the way back up. And so the thing that was invented is basically a little weight. So at the top, you lower your bottle over the side, and then you drop, when it gets to the right depth, you drop a little weight. And if you get it right, and we still do this manually sometimes, the weight whizzes down the line and then it hits something and that snaps the top and the bottom of the bottle shut. And then you can haul it all the way up and you've got a sample of what the water was like at that depth. And that was our access to the inside of the ocean. And now there's much more sophisticated. Now you get rings of them and it's automated. And, when I was describing sending something over the side and you see the temperature and salinity layers, what you actually do is you send it down and you map out the layers, and then on the way back up you choose the time to close the bottles so that you can collect water samples from specific layers. So that is the physical oceanography workhorse until really very, very recently. That's how we understood the inside of the ocean. So you're looking at thousands of point measurements. It's like looking at the Sistine Chapel and only being able to register, 1 or 2 pixels for every sort of 3 meters you go along the ceiling. But still, you could map things out. And then alongside measurements like that, people did try and go down. It's obviously hard to send humans, but William Beebe in his Bathyscape in 1932, I think, went half mile down. That was what his book was called. And so humans did start to try and go, but it was a very exotic environment, and you're very limited in what you can do because of the pressure. So, and then a lot of biology was done just by scooping things up in nets. And so it's like studying ecosystems by studying roadkill. You get the picture, but you never really see how this thing actually walked or ran or ate. You just see the kind of squished bits that get brought up in your net. So oceanography was very primitive for a long time, and it was just kind of a brute force effort. And it's only really in more recent years where satellites give us global coverage of the surface, no penetration basically, but you can see the big patterns. And then we're starting now to get autonomous vehicles, and there've been floats. That's the other thing. So there's an amazing system called the Argo floats that is one of those lovely examples of international cooperation actually working. So an Argo float is about 1 meter tall. It's about the width of and it's about 10 centimeters in diameter. I guess it's yellow. They're all yellow. And it's a kind of tube that goes up and down vertically in the water. So every country does this. Every country that contributes lots to oceanography does this. So people go out in the research ship. They have their Argo float ready. They just chuck it over the side somewhere, and then the Argo float goes down to, I think, 2 kilometers depth, and then it comes up to 1 kilometer, and it just floats for 9 days. And then it goes down again, and then it measures all the way up, and it pops up at the surface, and it phones home. And then it goes back down to 1 kilometer, and it sort of floats around. And so there are 4,000 of these in the ocean, and they're becoming more sophisticated with time. And they're great, but of course they don't get you into the really awkward places. Like they tend to be in the big ocean basins, and they tend to end up in the same kind of places. So things like that have helped us out a lot. And then there's just a lot of process studies at the surface. People like me who go out on ships and measure directly and then come back. And of course, all this now is tied together with computer models and theoretical understanding. And now there is starting to be discussion of many more autonomous. I mean, the joke about autonomous vehicles for a long time was that they didn't come back. You waved it goodbye. Maybe you'd see it again. Maybe you wouldn't, £200,000 worth of equipment. Bye. So yes, but it's a lot of it has been process studies. You go to study a process in one place because that's where you can really examine everything. And now we're still data poor. I think most oceanographers still think of us as a very data poor science, but we're starting to approach the age where that might switch, and we might suddenly have more data than we know what to do with. So it's a slow process. And of course, you're not just studying the physics, you've got the chemistry and the biology, and they all interact. You cannot just be a physicist in this space because the physics is directly affected by, the chemistry and the biology. And so you're sort of, it's very collaborative, actually. That was the thing I noticed most when I moved into ocean science from physics, or a bit more, into this, is that you can't hide what you're doing because you all have to do it together. You've got one ship, you've got one shot, you've got to talk to each other, and you've got to get on. And you can't hide away in your lab just doing something secret, because if you do the physics, it doesn't make any sense unless you also know what the biology was doing and what the weather was doing and what the trace gases were doing. And so it's natural. And of course, you're living on a ship with people while you do all of this. Yeah. So which is a very leveling experience. So yeah, it's an interesting. I think the way ocean science has got done is very different to a lot of other sciences because it has to be collaborative right from the start. You don't have a choice about that. Makes it a much nicer place to be honest.
The point about satellites is a really interesting one because I think people don't appreciate that that water in general is just not as transparent as you would like it to be. Before our conversation, I went to Google Maps just to see what it would show me if I looked at the ocean rather than, the local streets, et cetera. And interestingly, they have clearly cheated. They're showing us the topography of the bottom of the ocean, and this is not what you would see if you just took a satellite image.
Yeah, although interestingly, some of that is measured using satellites. So there are. This is one of those things that sounds bonkers, but apparently it does work. There are so. Obviously, having a lumpy seafloor means that local gravity points in slightly different directions, right? And so there is at least one pair of satellites that can go round and round the Earth, and they follow each other. But the distance between them alters ever so slightly depending on the local gravitational fields below them. So actually, some of that large scale early mapping of the shape of the seafloor was done by satellite, by inferring gravity. What mass must be there in order to make these satellites behave as they did. I can't remember the question you asked me.
That it's hard to see. And, the satellites are not really showing us an image of the
Yeah,
seafloor
but it's very
directly.
seductive, isn't it? It's very
Yeah.
seductive to think we've got these global maps, and of course we fill it in now using so reanalysis is one word for it, where you take your bits of data and then you stitch them together with a computer model effectively, and it all looks smooth and nice and lovely, and it looks like you know everything, and of course you don't. So satellites are useful, but as you say, light doesn't travel. And one of the things that is interesting about the ocean that is kind of obvious to a physicist once someone's mentioned it, but no one ever really talks about it, is that on land, for us, light is a long distance messenger and sound is a short distance messenger, because, you can't really hear another person across the street, but you can see the moon, right?
Yeah.
Whereas in the ocean, it's the other way around. Light doesn't, even though we think of water as transparent, light doesn't penetrate very far. Even in the clearest waters, you might have a couple of 100 meters plus a bit on a good day. But sound, at least the lower frequencies, can travel potentially a very long way. So sound is your long distance messenger in the ocean. And so we are also ocean blind because we are literally ocean blind,
Right.
that we don't see the messenger that could tell us what's happening in the ocean. And so one of the other reasons we've underestimated the ocean on the very long list is that we can't look into it. We can look into the sky. We can see clouds and we can see birds and we can see clouds going in different directions at different heights. We cannot look into the ocean. And this is one of those places where I think no one's really done a good job of this yet, but you can see it coming, that some sort of augmented reality goggles effectively that give you can stand on a cliff and look into the ocean, and it will show you a realistic sort of representation of what's, let you see into the ocean. And then I think we'll start to see it as a place. And so I think that conceptual shift is coming, but I don't know where the computer modelers are who might solve that problem and work on that. But they have not emerged from the woodwork yet, but I'm sure they're out there.
Well, I know when it comes to exploring outer space, most of the heavy lifting is actually done by robots and autonomous vehicles, but there's also some romance and something personally important to having human beings up there. I presume it's a similar story with the oceans. I mean, do you think we should have more emphasis on human beings or less emphasis on human beings?
And this is one of those things that, I mean, we have a debate that you also have in space, but in a different way. And it's coming at us because of the carbon footprint of what we do. So to take a big ship out to the ocean, to cross, to be moving at 10 knots, to move a global class research ship across the ocean at, 10 or 12 knots, you're probably burning around $35,000 of fuel a day. And it's a lot of money and it's a lot of carbon. And so if we're studying the planets and saying, we think everyone should treat Earth better, and could we all stop burning some carbon? There's a lot of questions about the carbon that we are expending. And so there's this push now towards autonomy. And I am very concerned about that, because I think one of the reasons that the ocean is special is that humans have a relationship with it. And in the same way that I did not study cosmology because I knew I couldn't have a relationship with the cosmos, you've probably got one in a very different way, but I could not have a relationship with the cosmos, but I could have one with the ocean, because I can see it and be in it and play in it. And if we take humans away from that, I worry that it will become a lot more like sort of a computer game.
Yeah.
And the thing is about the cosmos, I mean, and you may disagree on this, I don't know, but fundamentally, we're not really changing anything out there. We can look at it and we can see different things, but we're not actually doing anything that's going to influence it. Whereas in the ocean, we are definitely going to influence it. This is not a computer game, right? Yeah. We need to be connected to this. And so human history is full of, the book as well is full of these. I mean, the point of this book, The Blue Machine, that I wrote, is that the influence of the ocean is there on almost everything we do if you just know how to look. And you can see it in history and culture and trade and what animals do. And that all of that is a human relationship. And so, of course, we like to think of ourselves as objective scientists. And of course, we're going to do our objective science no matter what humans we are. And of course, that's nonsense, right? We choose the questions to ask, right? We choose what we're going to prioritize in the funding thing. Those are cultural decisions. That's not a logical decision. And so having a relationship with the ocean is the point, right? It is like, that's why it matters. It's because of our human relationship with it. And so I'm not against autonomy, and little robots going off and doing things. But I think if we stop sending humans to sea, it would be like not having the astronauts on the International Space Station, right? That can that have the overview effect, that know what it's like to zoom over these countries 16 times a day and not see borders, and they can come back and tell us about that, right? And in the ocean, it's the same thing. It matters that people are there, and it not only matters because of how we choose to do the science. It matters because one of the consequences of all the technology that we have in the world is that it makes us very arrogant. It makes us think that we are in control, and we're not, right? The planetary engine is bigger than us. We might be messing with it, but it's still bigger than us. And so the thing about working at sea is it humbles you all the time. The ocean literally and metaphorically slaps you in the face quite regularly, and it reminds you of your place. And I think that is a healthy thing. And as soon and that sort of and this is what I when I worry about when I look at a lot of the geoengineering world, people suggesting doing things in the ocean to mitigate climate change one way or another. Almost none of them have been in the ocean and have really experienced the ocean and really understand how complex and beautiful it is. And so because they see it as this kind of stick figure, they think, oh, we can just do this and we can just do this. And they don't see they don't see the potential downsides, and they're not humbled by this system, right? They think they're in control of it. And so I also think that being humbled by the ocean is a good thing. And of course, human history has, we have been voyagers on the ocean for centuries, and we have been humbled by the ocean, right? That's how it worked. And we had to work with it. We couldn't work against it because we'd lose. So we had to work with it. And so I do worry that it will be too easy for funding agencies to say, oh, well, we can just send the robots. It's safer, it's cheaper, it's, we can measure all the things. And you're like, but what about the things you didn't know the robot should be looking for? That takes a human.
All right. Well, having given the human beings their due, we can now do the fun part, which is talk about the physics of what is going on here. You provocatively named your book "The Blue Machine," and this is again in very compatible with the idea that things are changing over time. That it's not just a static thing. What are the drivers of this change? I presume that sunlight is one of them. Wind is one of them. Is this something that we can sensibly make a list of?
So the two fundamental rules of Earth are that the energy flows through and the stuff goes round and round, right? That's your starting point. So it is the case that the energy driving all of the Earth system pretty much is solar energy. So the heating from inside the Earth, which is the thing people tend to mention, is basically insignificant almost all of the time. So, it matters if you care about the heat loss from planet Earth or something on the scale of billions of years, but it doesn't matter for driving the engine. So it's all solar energy.
Okay.
And that does get translated. So if you heat up the surface and you then heat up the atmosphere, because the atmosphere, interestingly, the ocean is heated from above and the atmosphere is heated from below because light radiation comes through and it comes straight through the atmosphere until it hits the ground, and then the ground warms the air up from the bottom, so it's like a hot plate. So yes, and that drives wind. So the ocean is primarily driven by evaporation to some extent, because that's the thing that so the amount of salt in the ocean stays the same, but water comes and goes. So if you care about how salty the ocean is, to go back to the question of how dense it is, then what matters is the amount of water that's come in and out, because the salt is the same salt. It's just diluted more or less depending on whether it's been raining or whether it's been evaporating. So those processes are effectively determined by sunlight, because if you're away from the sunlight, it's cold and you can radiate more energy away. So wind drives a lot of horizontal motion, and of course that's strongly affected by the Coriolis effect. The planet is spinning, and so things tend to bend to the right in the northern hemisphere. And of course the ocean water itself is subject to the Coriolis effect, to such an extent actually that there are lumps in the ocean. So people might be familiar with this, these pictures of these big gyres, so these big kind of roundabouts, carousels. So that in the North Atlantic, there's a big carousel that goes around, and it goes around clockwise. But because it goes around clockwise, right, the water is moving, but it's in the northern hemisphere, so it's being pushed to the right. So it's being pushed into the middle of the gyre. and it is being pushed into the middle. And we know that because we can see there's a hill. And of course, water tends to run downhill, so it wants to run back out to the side. So you get this thing called geostrophic balance, where the forces, the Coriolis force pushing the water into the middle and up the hill, is balanced by the gradient making the water flow back downhill. So we can see that the Coriolis force has an effect because it's literally making a little hill. Now, that hill in the Atlantic is not very high. I think it's around 10 meters from memory. I don't quite remember, but it is there, and we can definitely measure it by using satellites.
It's a hill, in the water level, not on the ground level.
Yeah, in the water level.
The actual water is 10 meters higher than it should be by average.
Yeah. And actually, that's how we measure wind speed as well. So we get wind speed measurements from satellites, and it's not because they can see the wind. It's because the wind plays the same game, right? You push water along, and it moves because of the Coriolis effect, and so it creates a little bump, and you can see that shape change, and you can infer back what the winds were. So fundamentally, the ocean engine is driven by wind and the Coriolis effect, and then heat coming and going. And then that creates environments. So, for example, you get places where a warm current and a cold current come into contact with each other, and that is a really interesting place in the ocean because those two water masses are carrying different things. So one might have some nutrients that the other one doesn't. So that boundary between the warm and the cold currents is like a city. Everything, lots and lots and lots of things can grow there. They're very, very productive. So, for example, there are penguins, and this is just one example, but in our islands in the Southern Ocean, so sort of on the way to Antarctica, penguins live on those islands. When they leave, you've got a pair of penguins, a male and a female, looking after an egg. And the deal is that one goes fishing and the other one looks after the egg. And the one that goes fishing has to get fish and come back before the first one starves. That's kind of the rules. You've got a time limit. Yeah. You can't just swim around the ocean, hoping to find a fish. So what these penguins do is very specific, and they've been tagged doing this. It's super clear. When one of them goes off fishing, they swim 400 miles straight south, because at that point there's this massive wall in the ocean, this front between warm water and cold water. And so it's a very productive area. There's you've got nutrients contributing from both sides. There's lots of stuff, lots of material for things to grow. So it's a really productive place. There's lots of fish. So the penguins go straight there. They spend a week fishing and they come straight back. And they're looking for a feature in the ocean. So it's not just that the physics of it creates an engine. It's that the physics driving this engine then creates places. It creates structure within the ocean that is the sort of fabric on which the biology is built, because it provides conditions for the biology. So when creatures navigate across the ocean, we have this sort of picture of them just kind of going randomly, like us perhaps going for a Sunday stroll in the woods. Oh, maybe I'll go over there, maybe I'll go over there. Generally, that's not what they're doing. They're looking for features in the ocean that have been created by these physical processes, and they are predictable. And that is the key thing, is that there's these patterns that they may vary a bit over time. So there might be some little spinning features that sort of pop off, a particular current on average once a week or something. But the point is, if you go to that area and you wait, eventually you will get one. So it's generally predictable, even if for a penguin or a tuna, it's not specifically predictable. And so these patterns of the ocean are generally predictable because the ocean's been relatively stable. And as we are changing things, adding heat to the ocean, making it more stratified so that upper layer gets warmer, changing wind speeds and stuff like that, those patterns are changing. So the predictable place where that physical feature is might now be shifting, and the biology has to adapt to that. So it's not just, it becomes quite profound in terms of how, if we change the engine and it changes shape, and you then change the predictability of a feature that, it's like your local supermarket just disappears. You've got a problem. Yeah. So all of this is interwoven, and it is all based on the physics, but it's such a rich story, and we are part of it. Humans, we are not separate to this. We have traded in particular places and fished in particular places because of the features of the ocean, not because we chose to. which is always the idea, that everyone has. It's because there is this engine is turning underneath and creating the conditions for the things that we see. So, yeah, it puts us in our place.
Well, it's a great segue into the fact that we haven't really talked enough about the biology that is going on down there in the oceans. I presume there is a lot of it. I don't have any good handle on how much we know about the biomass, how it's distributed, how the various networks that keep it alive.
So biomass is actually quite an interesting one because there's a relationship that no one can quite explain, but that seems to be very robust, which is that if you take all the organisms within a factor of 10 in size, so you take everything between a centimetre and 10 centimetres. Actually, I think you do it by mass. So everything between 1 gram and 10 grams. And you add up everything that's in that size category in the ocean. And then you take another box next to it and you add up everything between 1 gram and 10 grams or 0.1 and 1 gram. So you kind of take these factor of 10 categories going down. And you draw a bar chart that shows for every one of those categories how much biomass is in it. It is the same to an extraordinary degree that you have the same amount of biomass between, I'm trying to remember how many nanograms the smallest one is. But anyway, some number of nanograms and 10 nanograms as you do between 1 gram and 10 grams. It's the same, pretty much the same amount of mass. And the only place where that goes wrong is tellingly the ones that humans can see. So anything that is big enough for a human to have fished out or murdered in some, one of the many ways we have, those ones that it drops off. But if you look back to historical records as well as we can, it seems that in history it was pretty much flat. So the biomass distribution is very, very even across the scales. And of course, what that means is that most of it we can't see, because this is true all the way down to sort of things that are picoplankton, tiny, tiny, tiny things, and most of that we can't see. So most of the biomass of the ocean is hidden from us, which is probably a good thing when you consider what we've done to the biomass on land. Just as well, it's been hidden from us. And the interesting thing about life in the ocean is that it lives very differently. Our sort of typical picture of life on land is a tree. And the thing about a tree is it's very large, it definitely doesn't move, and it lives for a very long time. And that's our kind of mental image of biomass. But in the ocean, it's not like that. There's a lot of single cells. Things live very quickly and die very quickly. There's no storage. So most of a tree is kind of storage, right? It's not living tree, it's just storage. Whereas in the ocean, everything is turning over very, very quickly. So although the ocean produces almost half of, the photosynthesis in the ocean is almost half of all the photosynthesis on Earth, the actual biomass is much, much smaller because it's all turning around and there's no storage.
I see. Okay.
So the structure of those webs is very different. You can scoop up a cup of ocean water. It's definitely got a lot of life in it. Even at many, many scales below the ones you can see, but it's turning over really, really quickly. And so so life kind of pops, you get these blooms and then they disappear and then you get a bloom somewhere else, depending on how the mixing has produced the right conditions. So life in the ocean is structured very differently, but then you get a lot of it in these places where the physics concentrates the conditions for life.
Well, that's what I was just going to follow up on. I mean, here on land, we certainly have deserts and rainforests, right? We have places where life absolutely flourishes and places where it struggles. Is there life everywhere in the ocean, or are there some places where it's happier?
There are definitely some places where it's happier. So out in the middle of the Pacific, for example, that's the only place where I've really put down a camera and seen the whole of the underside of a ship, because there's almost nothing growing. There's almost nothing living in the water to get in the way. And the thing that determines that is nutrients. So for living matter in the ocean tends to sink. And that means it tends to carry, on average, a lot of things are cycled around near the surface, but on average, nutrients sink. So basically the nutrients down below and the sunlight is up above. And so the places where you get productivity are the places where you can bring the nutrients from underneath up towards the surface. So, for example, one of the stories I tell in the book is of the the coast of Chile, the Humboldt Current, which is an extraordinarily prolific. It's a tiny section of the global ocean, but it has produced at various times in history around 40% of the entire global fish catch just from that very narrow strip. And that is because that's a place where you get an upwelling, where cold, nutrient-rich water from underneath comes up to the surface, and you get, it hits the sunlight, so you've got everything you need for life. So you get loads of life. But then there are other places, so out in the middle of the Pacific, where water tends to be sinking. And so there's no way for nutrients to come up, so that the surface is nutrient poor, and the particular nutrient it's deficient in varies depending where in the ocean you are. But then you don't get very much life because you haven't got the raw material for it. So again, that physical processes are very important in setting what can grow where. So there are vast deserts and there are highly productive areas, and there's a lot of in between. And the coasts, for example, tend to be very productive, which is very convenient for us, because you get sediment blown off the lands, you get lots of nutrients, you get, it's shallow, so everything gets churned up, so you can get nutrients back up to the top really quickly. But there are large areas of the ocean where there's definitely life, but there's a lot less of it. So there's enormous texture in the life. Yeah. And, people think that in the UK, one of our bits of history that we tell is the cod wars with Iceland, that there was this argument over who got to fish Icelandic cod. It's very long and boring. But the point is, the reason there are cod in Iceland is that Iceland sits at this kind of crossroads in ocean currents. And so that's why Iceland had cod. It's not that, the Icelanders really, really, really like cod. It's that they're sitting on top of this feature that, creates this. And so our own history is determined by what the ocean has been doing.
There is a feeling in reading your book that a lot of it, especially the early parts of your book, are less about what the oceans are like and what they used to be like before we human beings came in and started messing with them. How much have we messed with the oceans? What is the human impact there? I kind of know what you're going to say, but you know a bit more specifically than I do.
Well, yeah, before I get to that, there is a point about I think it's great that we're talking, it's depressing, but it's great that we're talking about the damage more. One of the problems is that we haven't really understood the system we're talking about. So people hear things are going wrong, and then what do? You panic, right? It's like a doctor telling you've got some disease with a very long Latin name and you don't know what it means. Does that mean I just shouldn't eat broccoli ever again? Or does it going to mean I'm going to die tomorrow, right? And so the reason for most of the book being about the way the ocean still is, actually quite a lot of it, is that this still is a wonderful, beautiful, fantastic place. We have not completely stuffed it up yet. We're having a good go. But there is still a lot of wonder out there. It's not dead by any means. So I think it's really important that we have a relationship with the ocean as it is and as it could be, and not just jump straight to the depression, because it gives us agency. Once you understand how the system functions, right, you can see the problems and you can see what to do about them. So in terms of what we're doing, yes, we are stuffing a lot of things up. The biggest problem for the ocean is that we're heating it up. So 90% of all the additional energy that Earth is accumulating because of climate change is ending up in the ocean. That warms that top layer, makes it more buoyant, makes it harder for nutrients to mix up from underneath, affects what can live there. So corals, for example, do very badly in warmer water. It's also deoxygenating the ocean very slowly because as you warm the water, it's the solubility of oxygen changes, so it tends to off gas. So there's about 2% less oxygen in the global ocean than there was in the 1950s. And then you kind of go down changing the structure of ecosystems through overfishing and adding pollution, creating regions of eutrophication. The thing is, that list goes on a long time, and it is very depressing, and it is very serious. But if you understand the structure of the ocean or how it's functioning, you can kind of feel, okay, I can see what to do about it. I'm not just being told, here's a terrible thing happening and you just have to watch the car crash. I can already see the way, what to do. And the interesting thing about the book talk, that I've given many, 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 many times now, is that the book talk is pretty much all about, here's how the ocean is. Isn't this thing wonderful? Every single question after every single book talk I have ever given has pretty much been about the damage we're doing, even though I never mentioned it in the talk, right? And so I think on one hand, I think that's quite optimistic because people care, but it also means they know enough. We know enough about what terrible thing. Once you understand what the ocean is, you can see.
Right.
And then the thing is, you have to care about the ocean enough to do something about it. So yeah, I think it's important to really enjoy understanding how beautiful and rich and intricate the ocean is, because that's what's going to make you care enough to take action.
I mean, are we taking enough action? Are we headed in the right direction, do you think?
Well, the good thing is that we are much more willing to talk about the ocean. And I think that is such an important step. 10 years ago, I remember, among all the other ideas I was pitching for various things, I would pitch things about the ocean and people would kind of go, do we want to know about that? Because they didn't understand there was anything to know. And now people come to me asking me to speak about the ocean because they know there's something to know and they don't know what it is. So I think that by itself is a really positive thing, that we now have a conversation, and we need more of it. We need to normalize talking about the ocean and how it affects our lives. When it comes to other action, to be honest, the biggest thing we could do to help the ocean would be to decarbonize as quickly as possible. So it's the same as all the other, it's the same root cause. And we are not doing a great job. The thing that's positive there is that the technology is becoming, so solar and wind projects are not only the cheapest forms of energy, they're the ones that get delivered on time and on budget. And so that's the way, that's a very positive thing for the future, is that it's already the better solution. So let's just, that sort of got its own momentum, and that's very optimistic. And then on a lot of other things, I think there's obviously a big culture war about whether we see the planet as something to use up, or whether we see it as something to maintain and to be stewards of. And we need to be quicker. The slower that debate goes, the less will be left by the time we do turn the ship around. And so that is pretty serious. So yeah, I like a lot of people in this space. My level of optimism depends on which day of the week it is, really, what the news was yesterday. And, if you care about the environment, the news in the past couple of weeks has been it's been more on the pessimistic side, I would say. I think there's a lot of environmentalists are concerned by the current direction of travel in the US. But the rest of the world is still, on this track. So yeah, I'm not really answering your question, but I think the thing that really matters is that every single thing we do that makes it better matters. Like, it does make a difference. And if we miss one temperature, if we miss 2 degrees, the next target is 2.01.
Right.
That we can always, it is just better. There really isn't a downside to getting this right in the long term. And so every single thing we do will make the world better. It's not a hair shirt exercise, right? It's about making it better. So yeah, very mixed on the optimism front, but we can do stuff. The day I'll lose hope is the day we can't do anything. And there is still so much we can do.
I don't know if you know Hannah Ritchie, but she
Yes.
was a former guest on the podcast talking exactly about this issue, that on the one hand, you have to be clear in terms of communication that when it comes to the environment, climate change, things like that, things are very bad, but they're not hopeless. There are things we can do. And, it's a fine line to walk, because people don't want to hear two messages that sound like they're not completely compatible with each other. They're willing to hear one or the other. And sometimes the world is a little subtler than that.
And the problem is that everybody is in a different place in their journey, and everybody, will wake up someday. On Tuesday, they might need to hear one thing. On a Monday, they might need to hear something else. And so a lot of this is about positive reinforcement. One of the interesting things I'm an academic at University College London. I have to teach like everyone else. And my teaching is now getting sustainability into the engineering curriculum. And I've realized that a lot of it is about how we look. It's about the quality of the debate. It's not actually about knowing different technical material. It's about the quality of debate that you're capable of having. And it's that how well can we deal with nuance and complication, and dealing with the idea that a solution might be technically perfect and a social disaster or an environmental disaster. And I think that the willingness to engage in that debate is the thing That's the thing we've got to be really good at, is this idea that you have a perfect solution and that it's perfect. And the thing is, there are no perfect solutions in a complex world. There's always going to be some knock-on effects further down the system. But we have to think about this like operating on a human body, right? When a surgeon goes to the operating table, the human has to stay alive. Right? There's a whole load of diseases that would be a lot easier to cure if you could sort of switch the human off, fix the problem, and then switch them back on again, right? And we don't do that with humans, and we know it's a very bad idea. And the thing is, it's kind of the same with the planet. We have to treat every intervention as if we were operating on a living patient, right? The system is still running as we make these changes. And so we have to acknowledge the complexities, right? Because you don't want someone, in the same way that you wouldn't let a doctor put mercury in your kidneys if you had kidney cancer, because it would kill the cancer, because it would also kill the rest of you. We have to acknowledge that when we have a solution that looks technically perfect on a narrow, in a narrow set of parameters, that we acknowledge that it might have unintended consequences in the rest of the system. And it doesn't matter how technically brilliant it is, it still might not be the right thing to do. And I think that if we get better at that debate, then we are well equipped to make this a better future.
Maybe to wrap up, rather than thinking about saving the planet or the oceans, we can be more specific and think about ocean science and its prospects. What do we need? What are the things that you would prioritize if you were the emperor of the world and you could allocate all that money to studying the ocean better?
I would love a map of energy in the ocean, which is mostly heat energy, because actually we're not very good at that. We've got the big picture, but the details of how energy flows around the inside of the ocean are really important for quite a lot of things that happens. And that's really hard to map. Like we can't measure it directly everywhere all at once. And so that would be an amazing thing to have, some kind of 3D actual measurement of where energy in the ocean is, and how the shape of that changes over time. That would be really cool.
Sorry, by energy, how do we quantify that? Temperature, velocity?
A mixture of one of those. So both of those two, basically. Okay. Temperature and velocity. The kinetic energy is relatively small, but it does matter, and they do interact. So it would have to be both. And then I think that one of the biggest sort of mind-boggling problems in oceanography is that there are so many living creatures, and they pop up and disappear. And if you're one of my colleagues who measures plankton, so the tiny little floating things in the ocean, you can measure in a patch and you can go 50 meters that way, and it looks pretty different. And the chemicals it's producing are different. And then you come back 2 hours later and it's doing something else. And so some way of getting a grasp on that amazing heterogeneity, it all comes back to, this picture of a homogeneous ocean versus something that's heterogeneous and beautiful. And it's the same for what I do, being able to measure oxygen concentration and carbon dioxide concentration spatially. So it's those sorts of things. I would love to be able to see how heterogeneous the ocean really is. That's my wish if I got to be world queen for a day.
Well, if they ask me my opinion, I'll put your name up for the short list there. Helen Czerski, thanks so much for being on the Mindscape podcast.
Thank you. It's been a pleasure.